So I'm just gonna kind of plink through this a little bit. Week 3 announcement. This is obviously last year's. I'm not going to mess with it. But I'm hoping all of this is true.
Yeah, that was the only one we got wrong too. So.
Okay. Oh, really? Okay. And what I'll do next week, we'll just kind of go over things that we struggled with.
The CO2. The question was, does CO2 provide energy in photosynthesis? It's not the CO2. It's the sun that provides energy. Yeah, photons provide the energy. The CO2.
Yeah, I think that's
helps to deliver it. Yeah.
So like, give energy. Well, CO2 doesn't give energy. It needs the sun for the energy. Yeah, you got one. Not a true false one?
Yeah.
I hate true false. I do. I look at true false and it's like, it's got to be 100% true to be true. But in most cases, it's never true because depending on how you interpret the question.
I try to avoid the true false myself. There might be a few kicking around this course still. All right, well, first of all, thermodynamics, we covered this a little bit in 101 and 102, but it's good to review it. And this little statement right here, I'm going to write that out. I'm going to go ahead and write these out mathematically. So the first law, there's a couple different ways to write it, but one is just the change in energy over the change in time equals 0. You can also write that is just E dot equals 0. Or you could also write it as the sum of all energies equals some, I'll just say E naught, some constant energy. Now, there are physicists out there that claim that there actually is 0 energy in the universe. If you add up all the energy, you get 0. And that, because our own interpretation, we're sitting here, sitting here on planet Earth, and one, pretty easy way to think about energy is just gravitational. So, I take this from here, pull it up here, and it drops. But you could also think, the mirror image, there's somebody else on the other side of the planet doing the same thing. And it's just a spring, and whatever energy you put in, you're going to get back. So it's just, there's really just fluctuations. It just sort of, bounces back and springs back. But overall, there actually is no energy.
The balance is 0.
The balance is 0. Because how much energy is there? You could start adding it up, and then, well, where did that come from? Where did that come from? You go all the way back to the origin of the universe, and there wasn't any energy then because there was no universe. And so, and the trick you get into is that, well, if we do observe what we think is positive energy, and in fact positive temperature, which we'll get to in a moment, well, maybe there's actually some negative energy somewhere else. And some people think, well, that's dark matter or dark energy, et cetera, and kind of fun to think about. But anyway, practically speaking, though, anytime you add up all your energies, they have to add to 0. So chemical, thermal, mechanical, electrical, et cetera. Second law. I've had a lot of fun playing with this one lately. Second law, you've got entropy, and first I'll just define entropy. Well, first of all, I'll define, and then the other issue is that you're going to have a hard time claiming that the sum of all entropy in the universe is 0. And there's a couple different ways to look at it, but I'm just going to write it this way. Any change in entropy equals the change in heat flowing through a system divided by its temperature. And I've given a few examples. Let me just give one really quick. I gave this talk. I've given this talk a few times. I'm going to go back to 2012. Actually, I think I've got this under talks. I gave this in 2012. I gave it in Bellevue. And here's the talk. I got a bunch of stuff in here. So I've been myself working on quantifying entropy, and I'll show you. Don't get a headache. So what I did here is just say that the change in entropy is the change in heat flow through a system divided by its temperature. And so what I did for just our own sun, this is how much power flows out of the sun. It's 3.8 times 10 to the 26 watts.
Every second.
That's
It's constant stream.
yeah, that's its power. Like, you know, you can look at a 100 watt light bulb, and this is well, it's 3.8 10,000 trillion watts. 24/7, 365. We only see a small fraction of that, obviously. But from there, what I try to do is say, well, there are about this many stars in the universe, and if you multiply those two numbers, you can say, well, the universe is radiating at 2 times 10 to the 49th watts. This is the average temperature of the universe. It's just right around 3 Kelvin. And so from there, if you just take your heat transfer rate and your average temperature, you can come up with the increase of entropy of the universe as 7 times 10 to the 48 watts per Kelvin. That's how fast the universe is becoming disorderly, just meaning that something that was sitting there in a star is now, flying out of it somewhere else. So this is the universal rate we just looked at. I then said, well, what's the rate at which humans are entropicizing planet Earth? Well, if you remember from NRGY 101, we all of our technological power sits at about 16 terawatts. So add up all the wind turbines, solar panels, coal-fired power plants, what have you. That is how quickly we're converting chemical, mechanical, radiant energy into heat. That's the delta Q right there. So that's the Q dot. So the 16 terawatts is that Q dot. How, it's the change of heat with respect to time. This is the Earth's average temperature, 298 Kelvin. So we can then see how quickly the universe itself is becoming entropicized or disordered. And what I did was I just divided by the estimated volume of the universe, and that's, you can go look it up, but it's large. It's a lot. So you're dividing a big number by another big number, and you end up with actually a pretty small number, 2.34 times 10 to the negative 32 watts per Kelvin per cubic meter. So that's the rate at which things are just diffusing and becoming more disorderly in the universe. On Earth, though, it's 1.7 times 10 to the 9th. Still pretty small, but it appears, at least, as if humanity is entropicizing planet Earth 7.6 times 10 to the 22nd times faster than the Earth would be doing that on its own. So it was a fun exercise. And is this going to mean anything down the road? I don't know, but it was just something, okay, I'm an academic, I get to do this, and we'll see what happens. So, yeah, okay. So that's a entropy example. So again, the other thing to think about here is that heat is always flowing. As long as there is a hot something somewhere and a cold something somewhere else, the heat will flow from the hot object to the cold object. No way around that. So the upshot is that the change in entropy with respect to time, let me write it one other way here, delta S delta little t for time is greater than 0. Now, I'm not a chemist, but I've sat in on enough doctoral dissertations of students, defending their theses. Typically the question comes from the committee: is this process driven by entropy, or is it driven by energy? So, in other words, in a flask, in a beaker, in any bioenergy system for that matter, is it the universe's tendency to become more disorderly that's driving that function or process, or is it the system trying to reach equilibrium? And I don't have in the classic example of chemical equilibrium is that before things are mixed, they're sort of up here, and then they sort of roll through, and eventually they're at the bottom. No more exchange can happen. So those are the two different ways to think of how a chemical reaction is driven. One is by increasing disorder, and the other one is by reaching a lower energy state. And typically, it's not necessarily one or the other, it's just which one is dominating the process. Okay, so that's how entropy and energy can be applied in biochemical processes. Another way to write this is that the change in entropy with respect to time is also greater than 0. Okay, and then the third law, we don't usually have to worry about this one a whole lot, but it just says that the temperature of whatever system you're interacting with is always going to be greater than 0, and that's just because, again, heat is going to flow towards a cold object. It's I guess I liken that to, I don't know, trying to sweep the floor if you're at the beach. You're sweeping the beach, but there's always like some more sand is going to blow in, or that water is going to flow up from the. You can never sort of make this perfect vacuum. There's something's always going to invade your space where you're trying to make 0 temperature. Okay. Yeah, I actually like this thing. There was a guy who built what appeared to be a perpetual motion machine. Oh, here's what I want to say about perpetual motion. At the macro scale, you can't do it. But on the other hand, if you look right down at the nanoscale, I mean, just take a look at any chunk of matter. Everything in there is still vibrating. If it weren't, it would be at absolute 0, which is a violation of the third law. So on the one hand, perpetual motion is impossible because you've always got friction to deal with. So in these inventions that Da Vinci is showing here, each one of these little bearings is always sort of sucking off energy in the form of friction. And I want to bring that home mathematically with one other thing that you guys probably read this paper already, but I want to point out one little mathematical bit that's really key to all of mechanics. So let me pop this guy out. This is the International Journal of Green Energy, 2008, and I try not to put too many equations in here, but right at the end, I couldn't help myself. There it is. So early on in our little discussion, I mentioned that perhaps there's actually no energy in the universe, it's just always the spring. So this guy right here, this is mass, and this is gravity. So mass times gravity, I left off the H part, because right here we're dealing with forces. So, work or energy is always a force times a distance. So I've left off, so this is a force equation. This is a force equation, not an energy equation, because the length has been left off. So mg plus cv plus k equals 0. This part right here is a gravitational spring. And so, getting back to Da Vinci's deal here, each one of these little rods, as they spin around, is moving up and down in a gravitational field. So you can never get back more than you put into your gravitational spring. Or the best you can do is to get all of it back. Where's the other spring in here? Well, it's just this. X is how far you pull the spring, and K is the spring constant. So I can draw both of those here. Spend a little bit of time on this. So mg plus cv plus kx equals 0. Well, so if we've got, and let's just say, oh yeah, here we go. And this is just the simplest mechanical system you can ever think of. So you've just got a mass sitting here. You've got gravity doing its thing, and the however far you pull this is x, and then this spring itself has a spring constant. So think of a garage door spring versus a spring in a doorknob, et cetera, et cetera. It's always some kind of force per unit length. So in this case, this is actually the sum of the forces equals 0. Okay, so this is conservative, like I just said. You're going to get back at most what you put in. This is also conservative. This guy right here, I haven't drawn yet, but this is non-conservative. Sometimes this is called an even term. This is called an even term. And this is called an odd term. Now, what is CV? Well, CV, and there's another way to draw this, and I'll draw a new picture too. It's a little clearer. So if we have instead our mass bouncing back and forth on a spring horizontally, of course you've got X, which is how far you pulled it, but you've also got V, which is the velocity of how quickly you're pulling it. Okay, and then of course there's no such thing as zero friction, so, and K is still here. In this case though, you've got C, which is just your drag coefficient. And where does that go? Well, it's just heat. It's just heat. In an engine, in bearings, in what have you. So at the end of the day, all of this energy that we're using actually goes to heat. And where does that go? Well, radiation, right? I mean, the Earth is always radiating its heat back into space. The issue we're having right now is that with the CO2 in the atmosphere, we're not radiating it as quickly as it's being absorbed. So, back to my little talk. I think I might have. Oh, yeah. Back to my little talk. These 16 terawatts are becoming. We've covered this in 102. These 16 terawatts are becoming basically 500 times 10 to the 18th joules per year of heat. You know, and then I don't know if you listen to the news, but there's like this big methane leak in California and the CO2, et cetera. That only adds to the problem because it keeps those 500 exajoules around longer. Okay. So there's some thermo for you. Another thing to keep in mind is that we're going to use the Celsius and Kelvin scale. The degrees or the spacing in those two scales is the same. So if you want to draw that, I think a lot of people think about this visually. So I'll just draw these two scales. Sorry, this is actually supposed to be a rectangle. It's okay though. You know, right here we've got, so we'll just do Celsius. Here's Kelvin. 0 Kelvin is the same as negative 273 Celsius. If we had, let's just say this is 0 and this is 100, basically all you need to do is say, well, gosh, since each degree Kelvin is the same as each degree Celsius, the only thing you need to do is say, well, gosh, I'm up here another 273. So water freezes at 273 Kelvin, and water boils at 373 Kelvin. If we go back to my other little slide, I said that the Earth's temperature is 298 Kelvin. So temperature of the Earth, you know, somewhere in there. So, yeah. So anyway, so that's your Celsius and Kelvin. And typically we deal with changes in temperatures. So 10 degrees change in Celsius is the same as 10 degrees change in Kelvin.
So it's a delta, like a delta temp, so it's
Right, exactly. Another way to write that is delta T in Celsius equals delta T in Kelvin. And if we want to get between Fahrenheit and Celsius, we can use delta T Celsius equals 5/9 delta T Fahrenheit. Okay. Because 1 degree Fahrenheit is only 5/9 of a degree Celsius. Oh yeah, CP Snow. Yeah, I love that. I was quoting this the other day and I couldn't remember who did it, but there it is. You can't win, can't break even, and you can't quit, can't stop playing. Cool. Okay. Efficiency, energy out over energy in. That's a big one in just about any process. I like to write it like this. This is just eta equals E out over E in. If you are writing up your term paper and you want to use the efficiency symbol, start with an H. Actually, while we're in here, let me just pop a little equation in here for fun. And here's what I typically do. I like to put in a tab in the middle, and then I'll put another tab over here. And so if I tab over, now I'm in the center, and I'm going to go ahead and insert an equation. And usually there's a few that are already kind of built in. I know I'm going to do a fraction, so there we go. What the heck? And then I think, let's see if it works in here or not. Oops. No. Anyway, within the, I'll show you how to do it in Microsoft Word in a second. But so within here, you come down. This took a long time to figure out, but under basic math, there's also Greek letters, and you can pick out the eta. There it is. Right. Equals. And now I think up here we're going to do energy out over energy in. So let's do energy over out. To move around inside this equation, I'm just using the arrows more or less. So I'm going to come down here, I'm going to use my mouse to click here, left arrow, shift E, right arrow, I. Right. Okay, I'm going to tab again, I'm going to open a paren, and now here's kind of the fun part. If you start putting equations in your paper, you can Let's see if I can find it here. I'm going to insert a field. And typically it's under this quick parts, which is hidden under this very generic looking. Might be somewhere else on different, but you're going to insert a field. And I like to put it in like so. I'll put it in as a sequence. And you can put in all kinds of sequences in your document. I'm just going to call this an equation sequence. And I'm going to hit OK. And it put the number 1 in there for me. Now I'm going to do the close paren. And I'm going to come down here and say where H is efficiency, E naught is energy out, EI is energy in. All right, so I'm writing my little scientific paper. Now, what I did, I wrote an H, but this is, in fact, the Greek equivalent for eta. And you can see I've got a little speed key to do that for me, but it's now a symbol. And what I also want you to do is make sure you italicize your variables. Italicize the E. This guy I'm going to do a control equals for a subscript. Control I, control equals for a subscript. And I'm going to say that's fine. I'm going to add that to dictionary. So there we go. And also, this, well, let me make this a full sentence. Efficiency is defined as eta equals E naught over E I, where eta is efficiency, E naught is energy out.
Just want to do with the tab 1 so you can reference back to the equation later.
Yeah, so, right, so let me do that. So if you want, the best way I've seen is to take this whole, both of the brackets and the number and insert a bookmark. And I'm just going to call this efficiency. I'm going to add it. And now I can come down and insert, I think it's just a reference. Insert a cross-reference. There's all different types of cross-references, but bookmark is one of them. And there's the one I just made. I'm going to insert it, and it's equation 1. Now, if I want later, and this will help you in your report writing, so I'm glad I'm doing it right now. Bioenergy 244. Efficiency is defined as. The nice thing about this, if I want more equations, I can just copy this whole thing. I can come down here, I can paste it, and I didn't put in a new anything. It's a field, and it updates automatically. Like, maybe this is energy or whatever equation 2. So, and I could also take, if I had another one, get super fancy, copy this thing, come up here, paste it, update field, that's 1, update field, that's 2, update field, that's 3, come down here, update field, and it's 2. So I'm not typing the 2s, it just keeps track of it for me. Yeah, so it's fun little tips and tricks in Microsoft Excel. I love it. Okay. All right, here's another one, and this is something we're going to have to wrap our heads around together. Well, there's a couple concepts. Let's actually look at CHP, combined heat and power processes. So, and you can think of your automobile engine as combined heat and power. Like you burn the gasoline to power you down the road, but you're also you turn on your heater. And it heats your seats, or heats the air, or heats the windshield. So in a lot of ways, an automobile is combined heat and power. The biomass itself, we want to run as combined heat and power. It makes electricity. It makes heat. Just about every machine does. I think every machine does. And we also want to capture the CO2 and pump that into the greenhouse. So that's what CHP is. Okay. Now the heat rate. Let's look at this one because I sometimes struggle with this one myself. Heat rate. So let's get a new sheet going. Heat rate. Equals, and let's just come right back to the shell. Heat in over power out. Okay, we can do that. Heat in over power out. Now, for me, the best, again, we can just go right back to the automobile. Because what you're doing, so here's a model of a car, right? So you've got chemicals coming in. You've got O2, you've got C8H18, all right, so that's your oxygen from the atmosphere. There's your octane in your automobile. So here's your chem coming in. What happens to it next? Well, it burns, it gets hot. Engine. And the engine, I'm just going to throw it out there. I'm just going to say the engine is operating at 600 Kelvin, just as a round number. Obviously, some parts are hotter, some parts are colder, but it has some average temperature. I'm just going to say it's 600 Kelvin. And so this is thermal. In fact, I do have an example of this I can show you too. And then what you want, obviously, is mechanical coming out. And the power coming out in this case is P equals force times velocity. So the force is how hard the car is pushing against the ground. The velocity is how hard it's moving. So for the heat rate, where's the power out? Well, it's right here. Where's the heat in? Well, it's right here. So the question is, how good a job is the heat, because you're setting something on fire here, how good a job is that doing at making power? Yeah. So what you'd like to do if it's a and again, let's look at the units, because this is what can get a little bit confusing. This is BTUs per hour, and this is kilowatts. So let's go back and do a little unit analysis on this equation and make sure we're all on the same page. And then we can determine what the units of that thing are. And what is stated is this bench is the inverse of the standard efficiency ratio. So it should be that we've got energy out over energy in. Already looking at it, we go, well, that's not energy, that's power. But the question is BTUs per hour power as well? So let's go back to our little deal here, and I'll write it up again like this. I'll just write HR equals BTU per hour over kilowatt. Now, this kilowatt, in the case of our biomax, our 2,500 kilowatt biomax, you can think of this as electricity. The way I've done it here, it's in a car, it's, well, a conventional automobile is mechanical. All the new battery electric hybrids, they're more electrical. But either way, this is in fact power on the bottom. The question is BTUs per hour power as well? And the answer is yes. A BTU is a unit of energy. So we've got energy over time equals power in over power out. So if we go back and compare that to efficiency, it's the inverse. So in the case of efficiency, it's always going to be between 0 and 1. In the case of heat rate, well, it can be between 1 and infinity. If you had a perfectly efficient system, it would just be 1. You know, if in equaled out, so I'll write that as well. You know, if perfectly efficient, eta equals heat rate equals 1, right? If perfectly inefficient, eta equals 0, heat rate equals infinity. And give me an example of a perfectly inefficient system. I can think of one right now.
Probably burn a forest fire, right?
Forest fire would not be a bad example at all. Yeah. Yeah, you get all this heat's going and there's no work coming out. There you go. Forest fire is a good one.
We can't have a perfectly efficient system, can we?
No, the second law prohibits a perfectly efficient system. I mean, you might say, well, gosh, if I've got a spring or a golf ball bouncing in a vacuum somewhere, it's never going to die. You know, and the weird thing about it is, if you believe my little perpetual motion about things are always sort of moving at the nanoscale, you could think of the whole universe as being perfectly efficient because it's still moving. The question is it accessible to us? Can we actually do something with it? Yeah. Another pretty good example of a perfectly inefficient system is just a car idling. You're sitting there at the traffic light, and yeah, this chunk, you're sitting there at the traffic light idle. Yeah, this is happening. This is happening. That ain't happening. 0 miles per gallon.
So if you need power out here, that's it.
Your efficiency is 0 and your heat rate is infinity. You're just making heat. Okay, how are we doing on time here? Yeah. Okay, I'm going to take a break.